Hello, Flavio. Flavio. Hi, Flavio. How are you doing? Allegretti Ramos. Where are you located at? Ramos. Are you Hispanic? Ah, Brazilian. How you doing? Are you a fellow engineer or student? Yeah, in Brazil, they y'all speak Portuguese, right? And some of the words I understand, so I can understand a little bit, I guess, but probably not enough where I feel comfortable. So my last year PhD in the U.S. in the power. Oh, hey, congratulations! To get a PhD is not easy. It's very hard. And so you're looking. Oh, in the last year looking for a PhD in the U.S. Oh, okay. Electronic field. We might understand each other, maybe. Haha. Okay. So you're right now you're in Brazil then, but you're looking to the last year looking for. So you want to do your PhD in the U.S. in power electronics. Yes, it's PhD is very hard. Do you have your master's by any chance? If you have your master's, it becomes a little bit easier. Oh, you do have your master's. Oh, that's good. Yeah. Oh, no master's yet. Okay. 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 So it's. I think the master's is 30 hours for your master's, and then after your master's, uh, I think you need about 48 hours after your master's. So it takes quite a bit of time. I think if you go from your master's to PhD, it takes about 3 or 4 years. Uh, but don't if you want to get your PhD, uh, I recommend that don't give up. It's a long journey. It'll take a little bit of time, but I think it's worth it to get your advanced degree. Definitely worth it. Uh, it's hard, but if you take little steps, a class here and there, or whatever they require, then I am sure you can do it. Yeah, I would recommend. Uh, you know what? This is what I would recommend. Okay, if you have your bachelor's already, uh, if you want to, you can probably find a job. Okay, and most employers they have employee tuition. They have employee reimbursement. So a lot of companies will pay you to get your master's. Instead of you paying, uh, the company will pay for you to get your master's. You save a lot of money. That's how I did it. I I used to work at Sony Semiconductors. They paid uh, for I guess 2 or 3 years, and then I went to Southwest Research, where I'm presently at, and I continued my studies, and they paid continue paying for it. So I would probably recommend that if if you really want to get out, find a job with a big company that has tuition reimbursement, and what you get is you're gonna get uh, you're gonna get experience. That's the first thing. And if you're new to the industry, let's see. Well, yeah, if you work and they pay for it, it's kind of like a scholarship. I think uh, I went to the University of Idaho, and I think my total tuition, everything was like 20,000. Uh, but I didn't pay anything. The company paid for that. So if you find a job that will pay you to go to school, get your master's, it takes longer because you can take maybe one or two classes at the most, and it's a long trip, but you save a lot of money, and then you start working immediately because right now you have a lot of knowledge, but you don't have a lot of practical experience. Probably, maybe, maybe you have a lot of experience, but if you go work, then you start getting in experience, and then look for some of the older guys that are willing to teach you. Because a lot of times it depends. Some people don't like to share their knowledge because of job security. Uh, you know, they won't tell you a lot of the technical stuff because they want to keep some of the knowledge to themselves. But if you find someone within the company, then you can latch out and maybe you can get a someone to mentor you. So that would be the best scenario. Okay, you say I work on power electron. Oh, so you're working in the power electronic field. Oh, good, man. You're doing it. You're doing good on drone control and power supply management. Wow, that's pretty good. Excellent, excellent. Well, does your company do they offer employee uh, reimbursement? Will they pay for your school? It'd be nice if they pay for your school. If not, you're gonna have to. They don't. They pay. They don't. I don't think they pay. Find out. Almost a lot of the schools, uh, a lot of the employers do have tuition reimbursement. I don't know if it's in, how it is in Brazil, but I would think that if it's kind of like a way of keeping you as well, and you get better in doing your job. So I would investigate, see if they pay for that. Oh, okay. In Brazil, there are public universities, so it's free. Really? Okay. Here in the U.S., both undergraduate and graduate. Wow. See, so I didn't know that. Wow. Okay. So do you have to then pass some kind of a test to show that you have the aptitude, and then you get the free tuition, or is there some kind of testing that you have to pass? Oh, so you have to pass. Wow. There's a national exam. Oh, I bet that's tough. Wow. You have to be approved in that process. It's like, wow. Wow. So so you already gone through a big pre-selection. Uh, yeah, yeah. So you're not. I did not know that. I wonder. How about there's two other people online. If you want to introduce yourselves and what country you are uh, and does your country in your country is the university free or do you have to pay? I'd be interested in learning that. Here in the U.S., sometimes it's free if you have financial need, but for the most part, you we have to pay for that. Sometimes, if you get really good grades, you get a scholarship. You get paid free tuition. Flavio says, by the way, may I ask you something about DC to DC? Sure. Hi, Wang. Caillou Wang. Hi, sir. I am in the U.S. now. Oh, that's good. We're in the U.S. Oh, and by the way, Flavio, yeah, you can ask me a question. Hopefully, I'll be able to answer your question. Oh, you're from Wang is from China. So in China, uh, the universities, I'm assuming that it's free. And Edgar Collazo Reyes. Hi, Collazo. Señor Reyes, ¿cómo estás? Where are you writing from? Bien. Oh, that's good. Oh, you're here in the U.S. Oh, cool. Okay, so Edward is in California. Are you working in the field or are you a college student? I'm sorry if you see me rubbing my eyes. I've been working outside. Been working on my. I have a swimming pool, and I kept losing a lot of water, and found out that on the bottom of the side of the swimming pool, it's got a big crack. So I drained the pool, and I've been working on it. And right now in Texas, we have very hot weather right now. It's about 104 degrees, and and the swimming pool, the empty swimming pool reflects a lot, and I didn't use sunglasses, so my eyes are, I guess, it's burnt, and they kind of hurt a little bit. So if you see me rubbing, that's I'm in pain right now. But anyway, okay. So going back, so okay, Flavio, on that, let me address Flavio's question. 30,000, no, 30,000 kilowatt converter. Wow, you're that's a power area that I'm not familiar. That's a lot of power. Uh, 300. What's I work in the space community. We do power supplies for NASA and ESA, European Space Agency. And in space, there's not a lot of power. So the highest power rating that I designed is 200 watts. So when you say 30 watts, that's a lot of power. So I'm sorry, I'm not familiar with that. Uh, I'm not an expert at that. I'm sorry, Flavio. Usually, if you're gonna have, it says thought of interleaving. Usually, when you want power, you interleave uh, power supplies. Where you, let's say, if you have two power supplies, you can drive them at 180 degrees out of phase, and you get more power out of that. Okay, so let me see. Wang, it says, Edgar says, I watch your videos. Thank you. Wang says, I like teaching videos a lot. Thank you. Appreciate. I put a lot of time on those videos. I haven't done any videos the last 6 months. I've been really, really, really busy. So, uh, but hopefully I'll get back into it. Okay, Wang says I work on a lot of motor drives. Oh, okay. Yeah. So motor drives, that's like H bridges, right? Wang? And Edgar says IGBT. Yes, insulated gate bipolar transistors. Yeah. So your what is the price on that 30 kV? What is the input voltage that you're using? Oh, it says sounds like automotive. It's for a six rotor drone carrying 120 kilograms of payload. Hey, Fabio, I got a question on that drone. Is that like for military purpose? I know in Ukraine they've been using the drones to fight the Russians. That's, I mean, that technology has really taken off quite a bit. It's a six rotor drone. Wow, six rotors. A question: the more rotors, does it get more noisier? Does the propellers make more noise, or is it more silent? And 120 kilograms. That's quite a bit. Wang Wang says yes, three phase full bridge. Wow. So then you're talking a lot of power. You guys are working with a lot of power. Okay. Bobby says that the input voltage is 300 volts. I want to step it up to. Yeah, then you would need a boost. That's for sure. Wang is for synchronous motors. Yeah, it is. Ah, for military. It's quite noisy, actually. Wow. Wow. That's that's quite a bit of power. Okay, so if it's on the drones, how do you get the 300 volts? Do they stack a bunch of batteries to get the 300? Oh man, thank you guys for sharing our this. This is very. I mean, I'm learning from you guys. You're working in a different industry that I'm not familiar, so I'm being educated by you guys. I appreciate you guys. So we cannot get very close to the drone. It's hovering. It looks like it would be a tornado running. Wow. Reyes. So we have Ramos and Reyes. Okay, my application is for high voltage isolated. We deliver 25 watts, but we need a isolation barrier rated for 1.5 kV and can withstand transients up to 10 kilovolts. Okay, that's interesting. Okay, Edgar. Oh, we use batteries, but the energy comes from combustion unit. Holy, so this drone, it has a combustion motor. I thought they were only electric. So this must be a huge drone, Flavio. The motors are electric. Oh, yeah. Reyes is saying, "Wow, this must be a big drone." Yeah, but the energy for the comes from the combustion engine. Wow, well, the combustion engine is going to be heavy. So I'm assuming the combustion engine is driving some kind of a generator, and those are supplying. Oh, okay. Dang, 300 DC is like yeah, it is. Oh Wow, you guys are doing some very interesting work, guys. Okay. Wow, batteries are large and cannot power the phone for more than 1 minute mostly. Oh, wow. This is very interesting. Okay. So, a ver, this is so cool what you guys are doing. Hey, Reyes. Okay. I do work a little bit of high voltage. So, what kind of output? Okay, 25 watts. And it says you need a barrier isolation barrier 1.5 and can withstand a transient of 10 kV. Okay, so what kind of output voltage, Edward Reyes, you- are you using? That would be interesting to know what kind of two separate designs. You have two separate designs. Tell me about it. I'm interesting. And Reyes, you said you're in California, or is it Wang? Oh, Reyes is in California. Reyes, yes. Okay, Northern California. Oh, you say Northern California, you're probably in Silicon Valley, right? San Francisco Bay Area. Ah, okay. I have a San Jose. Okay. Yeah, you're in a good area. There's a lot of high tech uh, companies in that area. So, all right. So tell me about your application. You have one for 5 and then 12, or you have a high voltage? Okay, Edward is asking, Flavio, the drones have a short time to work. Do they expect to come back? Oh, good question, Edgar. It could be like a suicide drone. So if that's the case, they would have to carry quite a bit of a load. And if it delivers the package, then it doesn't have to come back. Wow, interesting. Okay, so so this is a little bit more complicated. Yes, they're expected to come back. So they're supposed to deliver. Yeah, oh, yeah, vaya con Dios. It's a round trip. Yes, to deliver the package, come back and deliver another package or surveillance. So it's either delivering a payload or surveillance. Wow, man, the videos that I see, what's happening in Ukraine, and the things that they're able to maneuver and drop bombs right at the open hatch of the of a tank. That's like wow. Always contact on this it is shut down. Hey, I got a question, Flavio. Or I saw some videos. Some of the Russians, they had like it looked like some kind of a rifle, but it wasn't a rifle. And I could see them aiming it at the drone, and it wasn't shooting anything. Is it some kind of a like a jamming uh, device? I was just wondering if you knew anything about that. Do they get jammed? And what frequency do the communications do they operate? Is it in the high frequency, high gigahertz range? If you know any info, if not, just yeah. I thought it was some kind of a, I don't know whether they're jamming or they're doing some kind of a magnetic pulse to try to fry the communication. So I thought that was kind of interesting that they, and I'm not sure how well they would work or not. That is, wow. So Flavio, if you allowed, what company do you work? Oh, okay. Edward says I can't fully explain the application because it's for a company. Yeah, I understand. It's my first time working designing power electronics. I need to power a couple of boards on the main power path of the system. Okay, I fully understand that. So yeah, there's things that I can't. Some of the stuff I can't. I wish I could, but uh, a lot of the stuff that I have, it's sensitive, and there's a ITAR protected. It was really noisy. Okay, so Flavio says that it may be a magnetic wave, like one would try to cause interference in the plane. Okay, yeah. Well, it's some kind of electromagnetic that, or maybe they're just jamming the frequency to break the communication between the controller and the drone. And so Edgar says, I already have a design and it was really noisy. What was noisy? Oh, you're talking about the output ripple? The output voltage ripple was noisy? Okay. Oh, okay. Uh, Try this. Okay. How I have to tune the RDC pump on the primary, right? The RDC was in the primary? Okay. Okay, let me ask you, how did you measure your output ripple? Okay. Uh, because let's see. Okay, so here's a scope probe. If you're using this with this, okay, and let's say you clip your ground to ground, yes. If you put your ground and you clip it, and then you connect it where the capacitor is, this it's a big loop area, and it picks up a lot of magnetic fields. So this will pick up a lot of noise. You don't want to do that. Definitely do not want to do that. That's bad. So the proper way to measure your ripple on your this, you're gonna have a little bag, and there's a little spring. Yeah, that magnetic wire is very bad, and you might not have a noise problem. You might have a measurement problem. Okay, so what you want to do is take this off. Oh, okay, and see, yes, and what's a good bandwidth? Okay, you want a narrow bandwidth. Okay, so then you take take this off, the probe, take it off, and there's this little spring that goes right here. Okay, so now the loop that you had is much shorter. So this goes to ground. Okay, let's pretend. Oh, by the way, here's a high voltage scope probe. Okay. Uh, it broke and I'm trying to fix it. I designed this one, so I gotta fix it. Anyway, so let's say this is ground, and let's say this the middle is. So you clip that, you touch the ground to ground, and then you touch across the capacitor, and that will give you very good uh, a clean signal. So try that. This that's the proper way with this little thing. If you're using this, you're gonna get a lot of noise. Okay, so try that. See if that works. Maybe. Okay, here's another thing. If you're gonna measure ripple, you do not want a wideband a scope. Okay, Flavio, take care. He's going to bed. It's yep. Wake up. Yeah, tomorrow is a work day. I should have held this on Friday. That way you could stay up late. And it's already 11 o'clock. Uh, Good night, and thank you for chatting. I wanted to chat and thank you for sharing some of your very cool project that you're doing at work. And I wish you the best of luck. And it looks like you're doing real good. So, animo. Take care. Okay. Oh, anyway, yes, Reyes, yes, you gotta use a 20 megahertz. So there's a bandwidth. Uh, Most of the scopes have a bandwidth limit, and when they limit, it's 20 megahertz. So, so question is maybe why 20 megahertz? What's the reason that they limited 20 megahertz? I think there's a historical reason because of this, and I think I'm old enough. Okay, so when I started in electronics back in 1972 or 73, I think I was 12 years old. The Yeah, around the 70s to the 80s, uh, the band limit of most of the scopes back then on analog scopes were 20 megahertz. So I think uh, that was it kind of stuck around. And then also, the more bandwidth you have, the more noise the, the that you pick up. So yes, limited to 20 megahertz, and that should give you a better, uh, better scope plots without the noise. I think another thing that one of our design guys, Dennis Guerrero, he's been with Southwest Region for over 30 years. And I think for the common more noise that it's generated from the transformer, because there's capacitance between the primary and the secondary. So every time the primary is, going up and down, then the parasitics from primary to the secondary, there's a little bit of displacement current. Okay, so that displacement shows up in your output. So what Dennis does is he puts a capacitor from the secondary ground to the primary ground. That way, so you gotta think of it. If you there's a capacitor parasitic in the transformer from primary to secondary, you want that to return back to the primary, and by putting a cap from the secondary ground to the primary ground, instead of going all the way through the output, you return it through a shortcut. So that's one of the things they can do. Uh, okay, yeah. Well, the Y caps are usually you're gonna have your high line, your hot, and then you have your primary hot, and then your primary return, and then you have a chassis. Okay, the Y caps are usually go to your Y cap or to your chassis. So uh, you have that, and I think there's supposed to be special caps, or they may have some safety ratings. Uh, in space, our our bus is only 28 volts, so we might not be as stringent as commercial. I think commercial, y'all are hooked up to the power line. Here in the U.S., it's 120. In Europe, it's 220 or 250. So there's more importance that you have real good Y caps, uh, and I think they might be safety rated. So there might be some kind of rating for that. So I'm not exactly sure. I'll probably have to find out more on that. But yeah, hopefully, if your design is noisy, try those things and see what happens. Oh, how about EMI? Are y'all doing any EMI testing? Has it passed EMI testing? Uh, are you using a flyback, or are you using like uh, a forward converter? Because the uh, flyback, you will always have more ripple. Okay, yeah, you're gonna have more ripple. See, the disadvantage with the flyback, well, the advantage with the flyback is that it's low parts count. So, and there's no inductor on the output. So, to reduce the ripple, you have to rely on the capacitance. You gotta have enough capacitance, and the ESR of your capacitors have to be low enough. Okay, so basically, voltage ripple. Remember, voltage ripple is equal to the your output current that's going through the secondary times your ESR, provided that your capacitor is big enough. And so you would have to put a bunch of capacitors. Now, it is possible if you have, let's say, a capacitor, you could put, see, after the diode, you have a cap. You could put another inductor and then another capacitor. I think I've heard it mentioned that it's called a polish inductor, a polish inductor, a polishing inductor. I think that's one of the terms that my magnetic uh, coworker, Dennis Guerrero. You can do that. The only thing is when you compensate, if you're using a current mode PWM, and you should be using current mode for your projects, uh, not voltage mode. In current mode, it simplifies your compensation. It becomes a first order system. So, so this is what I'm getting at. On your output, you're gonna close. You're gonna have your sampling resistors, and then that goes to your air wrap. You want to make sure that when you connect your uh, to the output, you connect uh, to the diode section where the diode and the cap connect instead of past the inductor. Because if you sample past the inductor, then it becomes a second order system, and then it's harder to compensate. Okay, it screws up your compensation. So you you connect the compensation before the inductor in case you want to do a pipe filter. So that's a big uh, design rule. Do it before the inductor if you're using a flyback. So keep that. Okay, so it looks like you understand. So I see PM 830810. Hi, Robert. I love your stuff. I'm very thankful. Please be sharing. Hey, thank you. Appreciate you guys uh, watching my videos and been doing. Oh, by the way, guys, about 2 months ago, I checked my. It's called the analytics, and I only have I think 8,500 subscribers, but I managed to get 1 million views in 10 years. So that was a a goal or a milestone that I just passed a couple of months ago. One 1 million views. So and uh, and for your record, uh, I have some of the videos monetized, and YouTube doesn't pay very much. I get like $20 a month, so it's not you know it's enough to take the wife to lunch. So I do the videos not because I make money. I do the videos because, especially like at work, I'll learn something new, and a lot of times I'll come in and before I forget, I try to document it, make a video for you guys and for everybody, and also for me because sometimes I forget, and I can go back to my videos and I can say, oh, okay, that's that's the way you do it. Originally, the videos I started making the videos. You guys may already know this or not, but my son, he's a uh, he was born with autism, but he's a high functioning, and he got his degree in engineering, and I was tutor him in circuit analysis and network analysis and autistic, and I think I probably have some autism, so he probably got it from. Well, I know he got it from me, from my side of the family. So it's autistic, and it looks like a lot of engineers have autistic characteristics. They we tend to have, how can I say, focus and attention to detail. Or at least that's what I've seen. That some of my coworkers have those traits that they can in, intensely focus. But anyway, or you do things over and over again. So so a lot of times I would teach my son and he forgets. So that was one of the ideas. Well, if I put the lecture or on video, then he can watch it over and over again, and then they'll sink in. So I started doing some of the basic electronic uh, videos for him, and then I started teaching some of the classes that worked. The one that actually got me started was Troy Diaz. He works at John Hopkins APL now. But he's the one that told me, "Hey, why don't you put the videos on YouTube, and that way I can watch them at home." So I give a shout out to Troy Diaz. He's the guy that got me started posting them on YouTube as well. Let's see, thank you. But if you teach in school, you won't reach this people. Yeah, that's true. Actually, I have been I've been I've been a guest lecturer at the University of Texas at San Antonio, UTSA. That's where I graduated, and I believe the power professor Sarah Atmed. She's been real nice and invited me to uh, give a lecture uh, once a semester, and it's been pretty neat uh, uh, going to my school and give some lectures there. So yeah, I think putting on YouTube uh, exposes a larger audience. Okay, Edgar says, "Hey Robert, thank you for your help. Appreciate the video speaking. Otherwise, she's not too happy that I'm still working on Sunday night. I te veo, take care." Okay, Edward, I know what you mean. Yeah, it's Sunday. You should be with the wife. Spend some time. Okay, take care. Okay, Wang, Robert, what is the best way to learn planar transformer design? Oh, okay. Okay. Unfortunately, I don't have that knowledge. We do planar design. I have a coworker, uh, and I mentioned his name uh, several times. Dennis Guerrero. He's our magnetic guru. Uh, I would say that he probably has the most magnetics. I think he probably has designed the most magnetics that have flown in space. I know that Southwest, last I counted, and this is like 15 years ago, I think we had over 130 supplies flying in space. So, and he's designed all the magnetics, and he designs the planer. So I'll probably approach him. Maybe he can. Maybe I can get him to uh, do a little write up, or maybe I can even get him to do a presentation on magnetic design. Let's see. Lance Freed said, "Listen to YouTube video about we're trying to use number supplier to 5 buck converter." Okay, I think you may have emailed me Uh, and I apologize. I do get quite a bit of emails from all over, uh, quite a bit. As a matter of fact, yesterday I was talking to someone from Pakistan. He had a question on transformer design, and I think I stayed until 1 o'clock in the morning talking to him. And then this morning, one of my friends, Ali, Ale Crush, he had a question, and there were very similar questions on that. So yes, yeah, the leakage inductance, uh, and a good source if you want to read up on leakage inductance is Christopher Basso in his book. He has like three books, I believe. Remember, he had his first book. He came out. It was so big, and then he came out with the second edition, and now he has a big, uh, huge book. And in there, the way he treats the leakage inductance, he treats it like a well. You got to remember, you have a leakage inductance that's not coupled. It's a part of the winding of the transformer from the primary that doesn't have any energy, but it's carrying the current because it's in series with the primary, right? So, especially on the flyback, uh, when uh, when the energy is released, then the leakage inductor acts like a little current source. Okay, and the current source is whatever the primary charged it. Okay, so then that energy has to go back into the to the primary, and the primary you can model it uh, as a impedance. Okay, so basically the leakage is going to be the whatever the current is times the characteristic impedance of the tank circuit. So, but fly puck, I've heard it, but I haven't studied it. And I think you're the one. I think you sent me something. I think if you haven't, uh, resend it, or I can. Uh, my email is rbo. Hang on. RBOLA35618 at AOL.com, or you can look me up and at in LinkedIn, and you can send me a message there, and you can attach uh, schematics or whatever. I can take a look at it. Uh, so if you're trying to model that, uh, what you can also do is if you have a magnetic, you need to characterize your transformer. Okay, so so here's the low. This is a RF, and a you need access to a Bodhi 100 or some kind of FRA. Okay, so what you do is you measure your primary, and then with the secondaries, let's say these are the two secondaries. So this is your primary, and your secondaries are open, and then you measure, you short the secondary, and you measure the primary again, and whatever that is, that's your leakage. Okay, so what you can do is you put that in your model. In other words, you extract a model of your transformer. So you're gonna extract the primary and then the leakage, and then you also measure the the resonant frequency of both the primary, and then you measure the capacitance from primary to secondary. So if you model this correctly, then when you do a spike simulation, you're gonna see spikes. You'll see the low overshoot. So that's the best way to model that. Okay, so you need something. As a matter of fact, not sure. Let me see. I have my Bodhi 100 right here. Get that. Right. That's my Bodhi 100. So, and right here, I'm doing some measurements. Okay. So I'm actually doing a low impedance measurement, and this is a short calibrator. And I have here, this is a this is a resistor. This is 250 microohms. That's low. 250 microohms. Oh, this, okay, this might be interesting. Ah, okay, so with this, you can measure 250 microohms with the Bodhi 100, which is really, really good if you can get down to, if you need measurements. And sometimes you get it, especially if you're going to do a planar, you're going to have extremely low uh, resistance or impedances. Okay, let me see the time. I've been on for almost an hour. Wow. Okay. I'm going to go ahead and call it a night. Uh, thank you guys for thank you guys for stopping by and chatting with me. I really appreciate it. I learned a lot from you guys, from your work experience, and it's always nice to see what other people are working on, and especially the drones, the military ones, and the high voltage stuff like that. That is very, very good. So hopefully I'll do this again maybe next month, and I'm planning to do a video on input filter design. It's actually the lecture that I did at UTSA. So I'm gonna do a video, post that, and it's very informative. And I think I'm gonna do another video on the Body 100. I learned something new today, how to measure certain things. So hopefully I'll have some more new videos on other subjects as well. Alrighty, well, thank you guys. Take care. We'll see you next time. Bye bye.